Hey everybody, today we're going to take a look at something called implicit differentiation. So for the most part, I'm going to keep it pretty easy today, and we're going to take a look at just expressions. We're not going to look at any equations because I want to just get you the basics and get you guys comfortable. So really what implicit differentiation means is an equation doesn't have to be set in the form of y equals. And again, we're not looking at equations today, we're looking at expressions, but it's a way for us to derive without an equation being in a y equals format. So to get us started, what I'd like to do is give you guys a few different examples. Again, it's going to be pretty basic today, but I want to give you this sense of what's going on before we really jump into it. So for this first one here, we have the expression 3x squared. So what we want to do is we want to find the derivative d dx, right, of 3x squared. It's just the notation. Now, we're taking the derivative with respect to x. You guys know this as 6x, but what I haven't really been telling you and that you've really been doing, it's been kind of that thing that's happening in the background, but we don't really see it, is that right next to this, there's something, a dx right? This means the derivative of x with respect to x. Now, that derivative of x with respect to x, what do you guys notice? It's the same thing divided by itself. So when that happens, we know that that's really just 1. So this answer is just 6x as you've come to know it. Right, so the derivative of 3x squared is equal to 6x dx, or for us, just 6x. Now, this kind of goes back to, I'm going to bring you guys over here for a second. This actually goes back to something like this. What is the coefficient of x? Right? We know that there's really a 1 hanging out here. Right? It's just this dx is the same thing. It's there, but we don't write it because it's just 1 and we would see it all the time. So unless it needs to be there, we don't always write it in. Today you guys may practice writing it in, but not necessarily. Now don't forget, we also have an exponent that's 1 that we don't always write in. We also always have a denominator that's 1 that we don't always write in. But we can't forget about it because they do become useful and helpful throughout. So again, that's really what's going on with this dx thing right here. Is it's there, but nothing really happens with it, so we don't write it. Now, where it does become important is when we see y's. So if we're trying to find the derivative d dx of 2y cubed, the way that this would happen is the power rule, just like we're used to it. So it's going to be 3 times 2, we get 6y, and then we decrease the exponent by 1 squared. But just like before, we said, okay, dx, the derivative of x with respect to x. In this case, we're going to say dy dx. Now, dy dx is not, it will stay alone, right? We're going to leave that dy dx because that's not going to become 1. So our answer for B, using what we call implicit differentiation, is 6y squared dy dx, and that dy dx does have to be there. And that's the goal of today, is just getting used to writing that dy dx and keeping it in there. And then tomorrow we'll talk about why is this useful, how is it helpful, and really how to work with it. So again, today is just do it, get the basics, get the sense of writing the dy dx, and then we'll kind of bump it up a notch tomorrow. All right, so with this third example here, you guys have x plus 3y. So what we do is we want to find the derivative, d dx, of this expression, so x plus 3y. So the way we do that is we take the derivative of each piece, right? So the derivative of x is 1 dx. I'm going to write the dx's in today just so you guys get the sense of what's going on with it, plus 3. Now, power rule with y, the 1 goes to a 0, so there's no more y's, and we're going to have dy dx. So the final answer for this one is going to be 1 plus 3 dy dx. And remember, dy dx means the derivative of y with respect to x. All right, so that's going to be our derivative for C. For D is a little bit interesting because we have a product, right? We have x times y squared. So if we want to find the derivative d dx of xy squared, we're going to have to apply the product rule. So we're going to have to do our left function, x, times the derivative of the right function. So the derivative of the right function is, all right, we'll put the x in parentheses, 2y dy dx, plus the right function, which is y squared, times the derivative of the left function, which it's just x to the first power. So dx dx, it's 1 dx dx. Since we know that this here just becomes a 1 and times y squared, and we also have this x times 2y dy dx, we do have to keep that dy dx in. Our final answer, I'm just going to rewrite this right below, is just x times 2y dy dx plus y squared. We don't have to write that dx dx because it's just 1. So this would be our final derivative for xy squared. I gave you guys a few practice questions that model these four. There's one extra one on there just to see if you get, if you guys are doing well with this. The goal today is get comfortable with the dy dx's, get comfortable with the dx dx's. It's probably helpful to write them in today. And then we'll start to get, as we get more comfortable, you'll probably stop at the dx dx's. But again, it's just a matter of getting comfortable. Hopefully this helps you guys, and let me know how everything goes with your work tomorrow. Thank you.